So this is how we design our model here. The sketch on the left, you look from the side, we essentially just put two layers of different densities on top of each other with a 2 kilograms per cubic meter density difference, and then we prescribe a speed of 1 meter per second in the upper layer. The lower layer is at rest initially. Okay, we place this in a model domain of about 500 meters in length again, 100 meters deep. And what we use here as well are cyclic boundaries. So the left and the right boundaries are connected. And then you can see after time, so what's shown here is you can see the colors give you the density. Okay, red is the heaviest and blue is the lightest, and the transition between you can see with the different colors. Okay, and what also are shown are these arrows that illustrate the flow field, the velocity field. So let's have a look at that simulation. So right, you can see the mixing that's induced by this instability. Okay, it's a mixing if you're confused about, because that's not really what happens at the sea surface. If you have breaking waves, you don't get a mixing zone between the ocean and the atmosphere. Because of that effects that take place on smaller scale, in particular the surface tensions, you actually get drops, and the drops are heavier and fall and combine with the water. Okay, so there are other effects which are not resolved in this simulation here, but you can get an idea of this instability mechanism. So some interesting features is that this mechanism actually doesn't start at a small wavelength. It actually starts at a relatively large wavelength. It's nothing small turbulence that grows. Starts at a relatively large distance. Okay, this is Kelvin-Helmholtz instability.